Okay, you're going to take a look at page 177 and we're going to go over the quick check problems numbers 3 and 4. Let me share my screen. We are down here. Looks like it's out of focus. There we go. Okay, so in number 3, you've got fluorine, which is a halogen or a nonmetal, and it's going to exchange places with the iodine in the compound. How do I know that? You're going to look on the right-hand side of the activity series and you'll see that fluorine is here. Iodine is down here. Fluorine being the uncombined element would kick out the iodine in the compound. So since fluorine is more active because it's at the top of the list, then iodine, this reaction will occur. So what I'm going to do is I'm going to make a note off to the side that this is non-metal replacement. And this is fluorine plus lithium iodide. I'm going to go ahead and highlight the fluorine and the iodine because they switch places, and that means iodine is going to get kicked out alone, and then I'm going to have lithium fluoride as a compound that forms, okay? Now, iodine is diatomic, so what that means is I'm going to write I subscript 2. Lithium fluoride, if you look at the periodic table, lithium is a +1, fluoride is a -1, and you're going to end up with LiF. Then from there, you need to balance it. I would put a 2 in front of LiF to balance the fluorine, which means a 2 goes in front of LiI to balance the lithium, and now my iodines are balanced, okay? If you take a look at number 4, for number 4, we've got calcium, which is a metal, and then we've got water. So anytime that you've got a metal being placed into water, remember the active metals are the ones that will replace the hydrogen in the water, because you think of the water as hydrogen attached to a hydroxide. And if you take a look, remember up here, I had you highlight the 4 active metals, and calcium is one of them, which means it will replace the hydrogen in the water. So this reaction will occur. So I'm going to make a note off to the side that this is hydrogen replacement. So this is calcium plus, I'm not going to write this as water, I'm going to write this as hydrogen hydroxide because it will help you figure out what needs to switch places. So the calcium and the hydrogen get highlighted, the hydrogen gets kicked out alone, and then you're going to have the calcium combining with the hydroxide. Now, hydrogen being a diatomic element, we will have to write H subscript 2. Calcium on the periodic table has a +2 charge. Hydroxide is OH with a -1 charge, and you're going to end up with CaOH parentheses 2. Now, in order to balance this, you need to put a 2 in front of the water, and now you're done. Okay, so those are the single replacement reactions. Now, let's take a look at the next page at double replacement reactions. Double replacement reactions occur when we have a chemical reaction between 2 compounds and they're going to trade cations with each other. Remember that ionic compounds are made up of a positively charged ion known as a cation, followed by a negatively charged ion called an anion. So in ionic compounds, the cation is first, followed by the anion second. It would technically be incorrect if you put it in the opposite order, okay? Okay, now, there are 3 categories of double replacement reactions. The first one is a precipitation, the second one is a neutralization, and the third is gas formation. So when we're talking about, and I'm gonna highlight these in different colors just so that they stand out. If we're taking a look at a precipitation reaction, you're going to have 2 freely soluble salts, and they're going to be put into solution, and then their ions trade partners, and 2 new salts are formed, and one of which is not going to be very soluble. So that means that you're going to have a precipitate forming, and that is your form of evidence that a chemical reaction took place. Okay, so this one that's not very soluble, that is my precipitate. Okay, then we're going to have actually, let me highlight something before I go on to the second type. I have the wrong color. A precipitate is indicated by the symbol S in parentheses, which indicates that a solid formed. So here in this reaction, that little S right there after the silver, this reaction is a precipitation reaction. This is my precipitate. Okay, now let's talk about a neutralization reaction, okay? So in a neutralization reaction, that means you're gonna have an acid combining with a base, and the products are water and a salt. So if we come down here, the salt is composed of a cation from the base and an anion from the acid. And the hydrogen ion from the acid and the hydroxide ion from the base will combine to form water. What form of evidence occurs during a neutralization reaction? Well, there's going to be some detectable heat. So even though it's sort of minor, if you're holding a test tube in which a neutralization reaction happens, the test tube will start to feel a little bit warm. Okay, so you'll notice here that they wrote heat after this neutralization reaction. That's not typically done, but they're just doing that to emphasize that it's coming off when it occurs. So I'm going to take this and I'm going to draw an arrow down to here because this is my neutralization reaction. This is my acid combining with a base to form a salt and water. Remember, acids are going to begin with hydrogen. Bases contain a hydroxide ion. Salts are ionic compounds. It's a cation followed by an anion. And the cation came, and this may help you, the cation came from here, the base, it's right there. And then the anion came from the acid, right there, okay? Now, let's talk about gas formation, double replacement reactions. Sometimes we form a compound that is really unstable. And when it's unstable, it will decompose immediately into something different. So right down here, let me find a different color to highlight the gas formation equations in so it stands out. So I'm going to use purple. So for a gas formation reaction, we're going to have a product that is not very stable, and it spontaneously decomposes to form water and a gas, okay? The two most common ones, which I would expect you to know, are carbonic acid and ammonium hydroxide. I strongly recommend writing the chemical formulas for carbonic acid over here. So that way, if you ever form these, then you would know, okay, wait a second. I actually need to erase that and write carbon dioxide and water in its place, or ammonia and water in its place. Ammonia is NH3. Okay. Okay, so these are the gas formation. So I'm just going to draw an arrow and take this. I'm going to come down here. Okay, now let me show you these two examples. So this would be considered example number 1, and this would be example number 2 for our gas formation. So when we form carbonic acid, which is H2CO3, you would want to erase that, and you would want to replace it with water and carbon dioxide. Here's my gas, okay? If you form ammonium hydroxide, which is NH4OH, you would want to erase that, and you would want to replace it with H2O and NH3. There is your gas, okay? Okay, so let's take a look at some practice problems on the next page. Let's go to page 173 right here. And on page 173, we're going to predict the products of some double replacement reactions, and they mixed in with some single replacement reactions here. So let me highlight the H and the Fe here. This is a double replacement reaction because I've got two compounds combining. But this is actually an acid because it begins with hydrogen. And this is actually a base because it contains a hydroxide. So that means that this is a neutralization reaction, which is a special type of double replacement reaction. So I'm going to write Dr/neutralization here, okay? I strongly recommend you write this out. Anytime you have an acid, write the name of the acid incorrectly because it will help you figure out what needs to switch places. Like, don't write it as hydrochloric acid, write it as hydrogen chloride, kind of as if it were just an ionic compound, plus iron 3 hydroxide. Okay, I'm going to highlight the hydrogen and the iron 3 because those are going to switch places. You're going to form iron 3 chloride plus hydrogen hydroxide. You're going to look at your periodic table. You're going to look at the charges. You have iron 3 and chloride at Cl-1. So that's going to be FeCl3 plus, and this is your salt because it's an ionic compound. Hydrogen hydroxide is H+1, OH -1. So this is really HOH, which is just water. We need to balance this. I'm going to put a 3 here to balance the hydroxide and a 3 here to balance the hydrogen and the chlorine. And you're done. Okay. Okay. Let's go on and take a look at number 2. Number 2 is going to be a single replacement reaction because you have an uncombined element, zinc, and then you have a compound that contains a metal, silver. So this would technically be a metal replacement, single replacement reaction. Okay. And we need to check on the activity series to see if zinc, which is the uncombined metal, is more active than silver, which is in the compound. So if you turn back, zinc is here, silver is down here. So that means that zinc is more active than silver, and zinc will replace the silver in the compound. So what we will do is, let's write this out in words. Zinc plus silver chlorate. I'm going to highlight the zinc and the silver because they need to switch places. And then you're going to get your silver alone plus your zinc chlorate. When you kick out a metal and it's now in uncombined form, you're not kicking out an ion. You're just kicking out silver metal. So this is just going to be Ag. Zinc chlorate, if you look at the periodic table, is Zn plus 2, ClO3 minus 1. And there's your compound that you get. To balance it, put a 2 here and a 2 here. Okay, now let's take a look at number 3. For number 3, we've got ammonium sulfide and cesium hydroxide. Those are 2 compounds. That means this is a double replacement reaction. Okay, so I'm going to write this in words. This is ammonium sulfide plus cesium hydroxide. I'm going to highlight the ammonium and the cesium. And then you're going to form cesium sulfide and ammonium hydroxide. You need to look at the periodic table to get the charges for everything. Cesium is Cs plus 1, sulfide is S minus 2. So this is CS2S plus ammonium hydroxide is NH4 plus 1 and OH minus 1. So this would be NH4OH. But hold on a second. Didn't I, on the previous page, just tell you that if you form ammonium hydroxide, that is one of the substances that is unstable and it decomposes to form ammonia gas and water. So if you take a look back here, remember we noted it here. Ammonium hydroxide decomposes to form ammonia gas and water. It's totally unstable. So we can't write NH4OH. We have to write NH3 gas plus H2O. Okay. So now what we can do is we can attempt to balance this. So we've got 2 nitrogens here. So we could put a 2 here. You've got 8 hydrogens plus 1, which is 9. So this is 6 plus 2 is 8. And then I've got 2 cesiums there. I'm going to put a 2 here to balance my cesium, which changes my oxygen and my hydrogen. So that 2 also goes to the oxygen. So I'm going to put a 2 here to balance the oxygen. And then my hydrogens are 6 plus 4, which is 10. 8 plus 2 is 10. So now we're balanced. Okay. Okay, let's look at the very last one. For this last one, actually, this is one that I probably would never give you. And the reason I would never give this to you is because chlorine is a nonmetal and it's a halogen. And we are assuming that it is going to switch places with the sulfur, which is not a halogen, it's just a nonmetal, to make lithium chloride and to kick out sulfur. Let's cross out number 4 just because I would likely never give you something like that. I would have another halogen in the compound. So you would have something in the reading to follow, okay? Now what I strongly suggest you do is attend 8th hour to work on some of the problems in the review questions, numbers 3 and 4. I can tell you which ones if you come to 8th hour, and then you can check the answers with me or you can check them on Advantage.